Hi everyone, my name is Lily from New York University. In this video, I'm going to show the work conservation of three control policies, which is back pressure, capacity aware back pressure, and position weighted back pressure. Here we refer to BP as the back pressure, CABP as the capacity aware back pressure, and PWBP as the position weighted back pressure. By work conservation, we mean that control policy is not work conservative if no flow can pass the intersection despite the availability of capacity in the outbound arcs. For example, in this figure, the control policy at this subject intersection is not work conservative since it gives green to the eastbound phase. Despite that, no vehicles could actually pass in the intersection during this phase, even though that we have available capacity in the outbound arc of the northbound movement. So, in detail, the back pressure outputs the phase which maximizes the sum of all the movement of omega AB times mu AB. Here, omega AB is the max of QA minus QB and 0. So QA is the number of queuing vehicles at arc A. Here, mu AB is the saturated flow rate during the time slot. So here we assume the time slot equals to 10 seconds. Hence, the saturated flow rate of movement AB and the saturated flow rate of movement CD are both three vehicles. In this example, we have a number of queuing vehicles at arc A as 27 vehicles, and the QB is 12 vehicles, QC is 11 vehicles, while QD is 0. So the eastbound phase, in the eastbound phase, the only allowable movement is movement from A to B. So we have this equation equals to omega AB times mu AB. So omega AB is 27 minus 12, which is 15, and then timed by 3, which is mu AB, we have 45. And for the northbound movement, we have omega CD times mu CD. So omega CD is equal to 11 minus 0, which is 11, and then times mu CD, which is 3, we have 33. So 45 is greater than 33, hence we have the eastbound movement as the output phase of back pressure. We can see that back pressure is not work conservative in this scenario since it gives green to this eastbound movement. Uh, uh, and despite that, actually no vehicles could pass in the intersection during this phase. And even though we have available capacity in this north arc, so actually if it gives green to the northbound movement, we will have three vehicles passing the intersection during the northbound movement. So we will then look at the CABP. So CABP outputs the phase which maximize the omega AB times mu AB, while here omega B is no longer the max of QA minus QB and 0, but instead it's the PQA minus PQB. So PQA is the function of QA as shown here. We have the QA still the queuing vehicles at arc A, and CA is the maximum number of vehicles that arc A can keep. So we have, for example, here we have QA equals to 27, while CA equals to 32. And here QB is equal to 12, and the CB is also equal to 12, since the QB, I mean arc B is already fully occupied by the vehicles. So 12 is the maximum number of vehicles that arc B could keep. And here C or infinite is a big number, which this paper takes it as 500, and m is a coefficient. It's a coefficient which they take it as 4. So we will use these two numbers here too. So in the CABP control policy, we have the eastbound phase as the omega AB equals to 0.7 minus 1 maximized by 0, then we get 0. So 0 minus 0 times times by 3 is 0. And for the northbound, we have the omega, we have the PC equals to 0 and the PD equals to PC equals to 1 and the PD equals to 0. So we have omega CD equals to 1, and then we have mu CD equals to 3. So we have the 1 times times by 3 equals to 3. So 3 is greater than 0, hence we choose northbound phase as the output phase of CABP. We can see that the CABP is more conservative in this scenario, since it chooses northbound instead of eastbound phase. So for the PWBP, we have the output phase as the phase that maximizes the omega AB times QAB. So we can see the difference. It's no longer mu AB but QAB. So first, we can see there's still another difference in omega AB. Here, omega AB is a position. Sorry. It's a position weighted Q length, which each vehicle is weighted by its location. And the QAB is the actual number of vehicles that could pass the intersection in phase P. So it's no longer the saturated flow rate, but the actual number of vehicles. We can see the difference from the example. So in this example is the same example from the two previous examples. We have eastbound here. The omega AB is equal to this part. We didn't list the detailed location of each vehicle, but we list the final result here. So this part is equal to 15.1, while this part is equal to 6.6. Note that the CAB, CBC, and pi BC are all coefficient, but since we only have through movement in this simple example, all these coefficients are equal to 1. So we have the omega AB calculated as here, and for the QAB, since no vehicles could actually pass the intersection during the eastbound phase, so the QAB equals to 0. Then the final result is 0. For the northbound movement, we can see the this part equal to 4.9 and this part equal to 0, since we have no vehicles. So and then the QCD. The QCD is the actual number of vehicles that could pass the intersection during the phase of northbound. Since we have empty arcs, since we have empty north arc, so the QCD is actually equal to the mu CD, which is 3. So the final result of northbound phase is 14.7. Then the PWBP will choose northbound as the final result. We can see that the PWBP is also work conservative in this scenario. In conclusion, for this case, which we call case A, back pressure is not work conservative, while the capacity aware back pressure and the position with back pressure are both work conservative. We will then look at another two cases. This is case B. In this case B, we have an incident happened in the middle of arc B. So we will see that even since here is fully occupied, if you give green to the eastbound movement, actually no vehicles could pass the intersection, despite that the outbound arcs of the northbound movement is empty. So if a control policy chooses eastbound phase as the output phase, this control policy is not work conservative. And according to the calculation result, the back pressure and the capacity aware back pressure will both choose the eastbound phase as the output phase, while the position with back pressure will still choose the northbound phase as its final result. So in the case B, only the PWBP is work conservative among these three control policies. The final case is case C. So in this case, we have an incident happened here in arc A. Similarly, if you choose the eastbound movement as the phase, you will have no vehicles passing the intersection during the phase, since it takes some time for the vehicles to travel from here to here. And if the time is greater than 10 seconds, then during the time slot of 10 seconds, no vehicles could actually pass in the intersection, even if you give green to the eastbound phase. So any control policy chooses the eastbound as the phase is not a work conservative control policy. But according to the calculation result, we can see that the back pressure and the capacity aware back pressure will both still choose the eastbound phase, while the PWBP will choose the northbound phase. So also we can conclude that only the position with back pressure is work conservative in this case C. We also have a simulation demonstration for all these three cases. So we can see case A first. So the simulation is done in the net logo. We can click to run the model. So we will reset first. We will first run the position. We will first run the back pressure algorithm. So in this simulation, this intersection is the subject intersection, which uses the algorithm of the three control policies, and while this signal is controlled by fixed timing. So we will run the back pressure first. We will speed up. So we can see the vehicles are accumulating. Okay, now we can see that the back pressure will always give green to the eastbound movement, since the number of vehicles at arc A, at this arc, minus the number of vehicles at this arc, is always greater than the number of vehicles at this arc minus the number of vehicles at this arc. So obviously the back pressure is not work conservative in this scenario. Then we'll stop the back pressure and switch to capacity aware back pressure. We can see that the CABP will choose the northbound movement in this case. So CABP is a work conservative in this scenario. Then we will try the position with back pressure. Similarly, we can see that the phase switch between eastbound and northbound phases. So PWBP is also work conservative in this scenario. So we will then try the case B. Run in NetLogo web. Click to run model. So we'll reset first. Still, we will run the back pressure first. Speed up. So we are initializing. So similarly, we can see that the back pressure will always give green to the eastbound movement for the similar reason. Then we will stop and try the CABP. So still we can see the switch between eastbound and northbound phases, but the CABP will only give green to the northbound movement when the south arc is almost fully occupied. So we can see, so we'll slow down first. So you can see now, pause. So in this, you can see here. So in this phase, at this time slot, the CABP still choose the eastbound as the output phase, actually which actually have no vehicles passing the intersection. Despite that, there is available capacity at this north arc. So the CABP is not work conservative in this scenario. We will try the position with back pressure. We can see the position with back pressure will switch to northbound more frequently. So as long as no vehicles could pass the eastbound, during the eastbound phase, the position with back pressure will switch to the northbound phase. So the position with back pressure is work conservative in this case. So finally, we will try to see. So in this case C, we can see that we will run the model in NetLogo web and then click to run the model, and it's initializing now. So we will reset first and run back pressure first, speed up. So it's warming up. Similarly, we can see the back pressure will always choose the eastbound phase, and we will switch to capacity aware back pressure. So slow down. You see here. So at this moment, capacity-aware back pressure still choose the eastbound phase as the output phase, even though actually no vehicles could pass the intersection during the phase. Then we'll switch to position weighted back pressure. So the position weighted back pressure will switch to northbound phase as long as the as long as no vehicles could pass during the eastbound phase. So we can see frequent switch between the eastbound and north. So in summary, we have demonstrated that the back pressure is not work conservative in all these three cases, while the position weighted back pressure is work conservative in all these three cases. For the capacity aware back pressure, it is only work conservative in case A, while not work conservative in case B and case C. This is the end of the video. Thank you.